Joining everyone. We can wait a few more seconds since I see people still coming into the waiting room. Okay, do you think I can start? Okay, so I'd like to welcome everyone for joining this first conference. Today we will have the first conference of the new cycle of conference Vaccines Explained. I'm Sharuka Gab and I'm participated in the organization of this cycle as a member of Harvey MedSoc, as this cycle of conferences is brought to you by the collaboration of 3 student associations here in Pavia, which are Harvey MedSoc, Groupocast, and Coordinamento per il Diritto allo Studio. So as vaccines are becoming the most overwhelming topic in our daily life, we thought about organizing this initiative to try and bring more clarity into it, but also try and analyze the topic from different points of view, seeing different fields and aspects. So we will be starting today analyzing from a scientific point of view. We will focus on the immunological aspect of vaccines. While with the last conference, we will focus on the vaccines that are like the main vaccines that are in commerce in Europe and how they work. But besides the scientific point of view, we will also address the topic from different standpoints. We will have a conference analyzing vaccination from a historical point of view, talking about the history of vaccination, how vaccination came to be, and how it changed the demographic of the world, but also from bioethical point of view. We will ask like the speaker of the conference will try to answer the question, is it a moral obligation to get vaccinated? And we will also have a conference analyzing the topic from a geopolitical point of view. So how are vaccines distributed throughout the world, and how is in general healthcare working, and the differences between different parts of the world and the political powers that are behind this. So we hope that through this cycle of conferences, you can get a more comprehensive view of the topic, and hopefully the speakers will answer to your questions and bring more clarity about it. And I will now let to the organizations that participated in coordinating this event to speak. We can start from Lorenzo Rubini, which is speaking from Harvey MedSoc. Then Eugenia Capozella will talk in behalf of Groupocast. And then we have Anna Katara, which will talk on behalf of Coordinamento per il Diritto allo Studio. So Lorenzo, I will leave the word to you. He's saying he can't speak. Is he muted, Simone?
All right, fix the issue. Thank you. Good evening, everyone. As Shuruk said, I am also part of Harvey MedSoc, which compared to the other 2 associations that are organizing this conference is quite young and quite small. We are an independent apolitical student organization, which was created in 2014 by Harvey students and for Harvey students. We are also slightly different from the other 2 associations, meaning that we are not a group of representatives. What we try to do with conferences, seminars, social events, charities, and sometimes also elective courses is to fill a void that we felt was there in the Harvey course. So in the medicine and surgery course, the English one, which is our overall aim is to unify the student body of the Harvey course by offering them support. It can be particularly stressful to study medicine in a completely different country, sometimes seas or sometimes even continents apart from your own country. Helping them with university, with the bureaucracy, with the typical Italian bureaucracy, but overall making the experience of the Harvey course more inclusive and more fun, both through our academic and our social events.
Thank you, Lorenzo. I think we can hear from Eugenia Capozzella now.
Hi guys, good evening everyone. My name is Eugenia Capozzella. I'm a year 6 student from the Harvey course and I'm a member of Groupocast. First of all, on behalf of everyone, I would like to thank Professor Maga for joining us tonight. It is an honor to have you speaking, so thank you. As the vast majority of you may know, Groupocast is an independent association born 15 years ago and composed by healthcare students. But our goal is not simply that of representing students in the different university bodies. We really believe in the possibility of creating a link between the community and between students. On one hand, making students aware of the different social issues that characterize the community life. And on the other hand, providing the community with scientific knowledge concerning the most important healthcare-related issues. So, sticking to our ideals and goals, we have collaborated with Harvey MedSoc and Coordinamento per il Diritto allo Studio in the creation of this cycle of conferences based on vaccines. We all know that vaccines are a pretty hot topic and they have always been a focus of major and contrasting opinions within the community. And on one hand, it is true that the knowledge was already weak, but we think that the pandemic has even worsened all of this chaos around the topic of vaccines. In fact, the pandemic has led to the urge of finding within a very short window of time a vaccine that had to be safe, effective, and against an agent that was largely unknown. And we are all very aware of the most recent safety-related issues that some of these vaccines have been facing. So having said this, the aim of these conferences is that to provide the community with knowledge that is true, that is valid, because ultimately the scientific truth is a single one. So I hope you enjoy the event. I hope you will join us on the following one. And I suggest you to follow us on our social media in order to be constantly updated on what we organize and to contact us whenever you have problems or whenever you have ideas. We will be more than willing to listen and help. Thank you.
Thank you very much, Eugenia. We can now hear from Anna Katara, speaking for Coordinamento per il Diritto allo Studio.
Good evening. I'm Anna and I'm part of Coordinamento per il Diritto allo Studio UDU Pavia. Coordinamento is a students' union, so that means that we, some of us are students' representatives in the body of the university, but we do not only do that. We organize also cultural events on topics like this one that we organize with Groupocast and Harvey MedSoc that made this event possible. And this is a really great opportunity. This is a really great opportunity because it makes the students aware and about this topic that is really a hot topic nowadays. I also might say that is a controversial topic because a lot of people don't know anything about vaccines. And with this event, we will learn a lot. And we will be able to share this knowledge with our friends, with our families. And this is a good thing because knowledge is what makes us active citizens and parts of the society. And so I think I've spoken enough. I'd like to thank everybody for this amazing opportunity and finished. Thank you.
Thank you very much, Anna. I would like also to thank all the associations that participated in the organization of this event. And I will now talk a bit about the conference of today. So the conference of today is How Does Immunization Work? It's the first conference of the cycle and it wants to deal with the immunological aspects that have to do with vaccines. So we will talk about the immune system, its response to pathogens, and also the application of this when we talk about vaccines. So the speaker that we have today is Professor Giovanni Maga, the director of the Molecular Institute in Pavia. He will walk us through the topic, and I really would thank you a lot for agreeing to participate. Your presence in our cycle of events and in the opening conference of the event is very appreciated, and we can't all wait to hear from your expertise about this topic. So I will leave the word to you, and thank you again for participating.
Okay, so thank you very much. Good evening. And I think for me, it's really a great pleasure to meet so many brilliant, interested students willing to listen to me, I would say. I don't want to say willing to learn, because I'm not sure then in the end whether you will think you have learned something or not. I hope so. Anyhow, let's start with some magic, meaning sharing the screen. You know, I'm pretty old, so for me, all these technologies is still amazing. Okay. Now, the topic of today, as you have heard just a few seconds ago, is how does a vaccine work? And I just, selected this picture. Maybe you are familiar with it. It's a humoristic vignette of the 19th century. Basically, at the time that the first variola vaccine was introduced, and it was derived from basically the bovine form of variola. And at that time, people were just, saying that injecting material coming from a cow will transform you actually in cows in many different ways. So that's a clear example of how, since the very beginning of the story, vaccines were, let's say, met with either hesitancy, if not really frightened or even complete distrust. And the reason why is that the basic question behind the vaccine is, I'm healthy and I have to inject myself with something I don't know, I don't understand, maybe I don't even want to understand, in order to prevent a risk that maybe will never happen, namely having some kind of infectious illness. So in order to answer to this question, which will be also part of your future profession, at least those of you that will become medical doctors, we first have to understand how vaccination works. And the purpose of a vaccine is to give you immunity. So in order to understand how does a vaccine work, we need to understand how immunity works. I, of course, cannot make a single lecture explaining all the intricacies of the immune system, but I will just try to give you a sort of overview of this very complex but fascinating system, which is the one that actually allows us to be alive, because without immune system we will all be dead, as you might know from some genetic diseases preventing the correct development of the immune system. Okay, so first of all, how many types of immunity do we have? We can distinguish two main kinds, the so-called innate immunity and then the adaptive immunity. So the reason coming behind these two different names is that the innate immunity is a sort of first line of defense, which is very quick, as you will see, but it's also very unspecific, and most importantly, it is not able to learn, while the adaptive system can learn which kind of pathogen is it facing, and then can react more rapidly the second time the same pathogen is challenging our body. Now, in the adaptive immunity, we can somehow speak about a natural kind, which is the one that we acquire after an infection, or in a passive way, the newborn baby who is developing inside the mother is getting through the a passage of the antibodies from the mother to the newborn, and the artificial immunity, which actually is not so artificial as you will see, but it's something that is induced by the treatment in an active way, let's say through vaccination, or passively through the introduction in the body of preformed antibodies. So innate and adaptive immunity are not independent, but in reality, we could not trigger adaptive immunity if we do not activate the innate immune response. So we will start our journey through the immune system from the innate immunity. What is it? Well, let's say basically it's the complex of all the obstacles, barriers, mechanisms that the body can put forward at the very beginning of an infection, starting from the physical barriers, for example, our epidermis or the mucosa, meaning that these are, say, layers of specialized cells that can in some way already reduce the number of pathogens that can find their way into our body. Of course, most of the time, these very same cells are those that are infected, for example, by viruses. And in this way, these pathogens can get into our body. And then they are recognized by specialized cell types, which are able to trigger a cascade of signaling that have, for example, the ability to activate cells that can kill infected cells. And then they release a plethora of chemokines, meaning small molecules, small peptides, that in turn activate the adaptive immunity and also trigger a series of systemic responses, for example, the inflammation, which are all part of this first line of defense. Because as you will see, in order to be activated, the adaptive immune response needs about 2-3 weeks, while the innate immunity can be active in a matter of minutes or even a few hours from the introduction of a pathogen into our body. So innate immunity is the first line of defense, and at the same time, it is required to trigger the more specific adaptive immunity. So now we will try to understand how these two branches of immunity work. Well, innate immunity, it might be unspecific, but it's not simple. Basically, it relies on a network of sensors, proteins that are present in many cell types, either in membrane-bound form, for example, on the cellular membrane or on the endosomal membrane, but also as soluble proteins. And there are very many proteins that can act in this pathway. And the function of these sensors is to recognize something foreign, some stuff that shouldn't be there. For example, large double-stranded RNA molecules. So you all know in the cytosol we have RNAs, basically messengers RNAs or microRNAs, but long double-stranded RNA is something that normally is not present in the cytosol of a healthy cell. But many viruses, they have a double-stranded RNA genome. And these proteins, they can specifically recognize this as a foreign element, which might suggest that something bad is happening into the cell. And the same is true for many of these other, you see, sensors. Most of them are recognizing nucleic acids, typically coming from the genome of viruses, but they can also recognize lipids or other components of the bacterial wall. Now, this sensor, they transduce signals into the nucleus at the level of DNA, and they activate a battery of genes, which in turn drive the synthesis of many different proteins. Some of them are required to make the cell an hostile environment for the virus. For example, synthesizing enzymes that degrade the viral RNA or that block, replication of viruses, or they can be secreted and fight the bacterial cells invading the tissue. But other genes, they are producing chemokines and cytokines, so small peptides that are required to trigger the systemic response, inflammation, and to activate the adaptive immunity. So you have to think about innate immunity as a network of molecular sensors that are able to recognize what we call the pathogen-associated molecular patterns, which simply means whatever is not, let's say, likely to be found in unhealthy cells, from foreign DNA, RNA to foreign lipids or proteins. Okay, now, one very important class of these sensors are the toll-like receptors that I just want to use as an example of how the system works. These are proteins that are membrane-bound, either on the cellular membrane or at the level of the endosomes. They are also in the endosomal membrane, will become clear later on in this lecture, because I will show you how endosomes can be the Trojan horses for many viruses to get into the cell. Anyhow, you can see that these toll-like receptors, they have very different specificities for different molecular patterns. So they can recognize peptidoglycans, lipoproteins. Of course, they can recognize also double-stranded RNA, but many, many different molecules that are specific for different classes of microbes. So while the innate immunity is not specific in a way that it cannot mount a specific response against a particular pathogen, like the adaptive immune system does, they are nonetheless quite flexible, and they can respond through these many different sensors to almost all kinds of microbes that can eventually find their way into our bodies. And the beauty of the system is also, a clear example of how evolution is shaping a protein in order to optimize the function of this protein. So, for example, this toll-like receptor 3, which is specific for double-stranded RNA, attains its specificity thanks to its particular three-dimensional structure. You see, it looks like, the hand of the extremity of an umbrella. And this particular shape, when the receptor is forming a homodimer, here it's shown embedded in the endosomal membrane, forms a site which is highly specific for double-stranded DNA. So double-stranded RNA. So single-stranded RNA, double-stranded DNA, they cannot bind because they cannot take the right interaction on these two opposing surfaces. So you see specificity, and this is true for all the toll-like receptor, is attained thanks to particular structural elements that are specific for binding a particular molecular pattern, a particular molecule. And again, this toll-like receptor system, which is one of the main systems of the innate immunity, is also extremely flexible, because the many different receptors, they can form either homodimers or heterodimers, and depending on the combination, they can, in the intracellular environment, bind different protein complexes, which can then trigger different kinds of signals. So for example, there are some combinations that are specific for inducing the interferon response, which is a small protein, and I'll quickly show you how the interferon works. While other combinations, they can be specific for triggering inflammation or both. So you see, depending on how many and which type of toll-like receptor are activated, you can have different kind of responses, which is an additional layer of flexibility of the innate immune pathway. So as for interferon are concerned, interferons are very important in the first response to, for example, viral infections, because by being synthesized in response to the activation of the toll-like receptors through this very complex cascade of signaling events, they can be secreted and they can bind to specific receptors which are present on the surface of many cellular types. And binding of the interferon to its receptor triggers again a cascade of signaling converging into the nucleus and then activating the synthesis of proteins, which in turn are devoted to block or at least slow down the viral replication by many different mechanisms. There are proteins which are turning off the whole protein synthesis program of the cell so that the cell will die, but at the same time will not produce new viral particles, or proteins and enzymes that can specifically bind to viral proteins or viral DNA or RNA, blocking different steps of the viral replication cycle. So interferons, and that's why they are also used sometimes in antiviral therapy, they can trigger the antiviral state of the cells. And all this happens every time a foreign antigen is introduced in our body, triggering, this innate immunity response. Another component of innate immunity is inflammation. Inflammation is very often thought as a bad thing, as something that is, very uncomfortable to have, to suffer. But inflammation is a very important defense mechanism because, for example, the increase in body temperature is slowing down the proliferation of viruses and bacteria, and also inflammation can increase the permeability of our blood vessels so that the cells from the immune system can pass from the circulating blood to the tissues where the pathogens is trying to multiply and then attack infecting cells or attack the pathogen itself. Of course, if the inflammation is too strong or is maintained for an excessive time, then it can cause damage to the normal tissues. And for example, one of the main mechanisms through which the SARS-CoV-2 coronavirus is causing severe symptoms is exactly due to a very high level of inflammation that is damaging tissues, particularly the lung tissue, triggering the severe acute respiratory syndrome or SARS. So inflammation is good, but too much inflammation is very bad. And many viruses can induce a very acute inflammatory response, which is part of the problem. So sometimes the main damage is due to inflammation rather than to the cytotoxic effect of the virus itself on the cells where it is replicating. This is something that you should keep in mind. Anyhow, once the innate immunity is activated, then the chemical signals that are, released by the cells that are activated by the foreign antigens, by the, the pathogens that are invading our body, and we will see in a moment how, will then send the right signal in order to activate the adaptive immune system. So adaptive means that this kind of immune response can shape itself on the basis of the particular pathogen that is triggering the response. And the main actors of the adaptive system are these classes of lymphocytes. The B lymphocytes, which are responsible then for the production of specific antibodies that will then bind to either the infected cell or the pathogen itself, and the T lymphocytes. And we have actually two flavors of T lymphocytes, basically. There are many flavors, but we can broadly, distinguish two main types: the helper T cells and the cytotoxic T cells, which are distinguished by a particular protein present on their surface. The CD4 protein is marking the helper cells, while the CD8 protein is identifying the cytotoxic cell. The job of the helper cell is to amplify the adaptive immune response, inducing the maturation and proliferation of the B cells and of the cytotoxic T cells. And the CD8 T lymphocytes, they are able to attack and kill the infected cell. Now, everything relies again on receptors, on proteins able to recognize a particular molecular pattern. But in this case, the molecular pattern becomes very specific. So we will have antibodies, T cells recognize it only a particular portion of a viral protein, for example, the so-called antigen. An antigen is, from a physical point of view, a peptide of about 20 amino acids derived from a protein coming from a pathogen. And this peptide is recognized by specific receptors that are present on the surface of the B and of the T cells. The B cell receptor is nothing else than an antibody, is the membrane-bound form of the same antibody that this particular B cell is encoding in its genome, and then once stimulated will produce and secrete. While the T cell receptor is sort of a half antibody, meaning that it has the portion of normal antibody which is able to recognize the antigen, because its role is not to produce antibodies, but to trigger a signal that either stimulate other cells or recognize the infected cells. So now we will briefly see how this apparently complex system, which is not only apparently complex, is extremely complicated, is working. Well, everything starts from the innate immune response, and the main actors in, let's say, joining forces between the innate and the adaptive immune response are the dendritic cells. These are very funny cells that can, move through the body thanks to these pseudopods. They are actually present in many tissues, and they represent the first line of not only defense, but of, let's say, guardian angels of our body. Because as soon as a pathogen is invading a tissue, these cells, they can phagocytate, the pathogen, destroy it, and then place those small portion of, for example, the viral proteins, namely the antigens, at the surface of the dendritic cells exposed through specific receptors. Now, these exposed antigens are the signals that are recognized by the circulating T cells, T helper cells, which are, let's say, in a naive state. So they have never met any antigen, but they are ready, and each T cell possesses a unique receptor able to recognize a unique stretch of amino acids. And basically, this system is able to recognize something like 10 to the 12th or 13th different kind of amino acid combination, meaning antigens. So whenever by chance these dendritic cells migrating to a lymph node, exposing an antigen, meets a helper T cell with a receptor able to recognize the antigen, then the signal is triggered and the whole adaptive system is then activated. And this is, of course, a matter of signaling, because the activated T cell is then releasing chemokines, cytokines, so small proteins that in turn stimulate the proliferation of all the other components of the adaptive immune system. Now, one very important, let's say, feature of the adaptive immune response is that we have, as I said, billions of different T and B cells, each with a particular receptor able to bind by chance, randomly, a specific antigen. But as soon as the receptor has recognized the antigen, then the signaling that is, activated by this event is stimulating the proliferation of that particular lymphocyte. So we have the clonal selection and expansion. In other words, if this is a B cell with an antibody recognizes a specific antigen, when the recognition is made, then this cell will multiply, giving rise to millions, even billions of cells, all of them encoding that specific antigen only. That's the monoclonal response. So each clone of B cells is secreting an antibody which is able to recognize a specific portion of a pathogen protein, for example, a viral protein. And this is very important because, as you will see, vaccination is doing exactly this kind of job, proposing an antigen in order to trigger the clonal selection and expansion of B cells secreting specific antibodies. And the same is true for the T cells. T cells that have a receptor which is engaged by a specific antigen will proliferate, giving rise to a population of T cells with that unique specific receptor for that unique specific antigen. That's why this system is adaptive, because it can adapt to a specific, let's say, range of antigens that are characterizing that particular pathogen. Now, all the system works through a series of positive feedback loops, because what we want to have is the amplification of the signal. So as I said, the T helper cells are very important because they are, giving the right signal in order to trigger those clonal expansion. And what happens is, for example, when we have a B cell which has engaged a specific antibody, this, specific antigen, this antigen, which is again a small peptide coming from a pathogen, is internalized, and the same is then exposed through a major histocompatibility complex, which is the way the helper T cell can recognize the antigen, making this immunological synapse, this binding, which triggers the release of cytokines, so small molecules that diffusing will induce the proliferation of this particular B lymphocyte and will, let's say, recruit additional helper cell, because of course many antigens will be recognized by many different B cells. So through these kind of events, the adaptive response is amplified through a positive feedback loop, which is strictly dependent on the T helper cells. Now, there is a particular viral infection which is hitting T helper cell, and this is the HIV, the human immunodeficiency virus infection, which depletes the body from the CD4 plus T helper cells. Now you can understand why HIV infection leads to immunodeficiency, because if you do not have T helper cells, you do not activate the adaptive immune response. Well, there's another magic the adaptive response is doing, meaning it can remember. You know, it's great that we can trigger a very efficient and potent immune response, specific, self-amplifying, very robust, that can suppress the proliferation of a pathogen. But it takes time. It takes about 2 to 3 weeks. Now, if every time we are challenged by the same pathogen, we need again 2 to 3 weeks in order to mount an effective immune response, that's not so good. That's why evolution has also included in this system a sort of memory cache. So every time a lymphocyte population, either B or T cells, is expanding through this clonal expansion that I showed you just before, a small portion of those cells will stay in the body as memory cells, meaning cells which are genetically programmed because they have been selected to express either a specific antibody against that particular antigen or a specific T cell receptor able to recognize that specific antigen. So the second time we meet the same pathogen, these memory cells, they can be immediately activated. And the advantage is clear. So you see, at the first challenge with the pathogen, we have the innate immunity, which helps to control the infection and triggers the adaptive response, which is, peaking around day 20. But then, if you have the immunological memory, the same challenge will again trigger the very same innate immune response, because the innate immunity is fast, but can also forget it very rapidly. While the memory of the adaptive immune response can give you a more robust response and also a faster one, which is peaking within 1 week. So that's clearly an advantage. And this also translates in a very high production of neutralizing antibodies at the second challenge. So you have the first encounter with the pathogen or the first round of immunization with the vaccine. Then you have production of your immunoglobulins. But at the second challenge, either because the pathogen is coming, or for example, when you need a boost of your vaccination with a second dose, then this is what happens. You have a very strong immune response with a very high, production of antibodies. So here you can understand the advantage of having an immunological memory. You can also understand why many vaccination protocols require more than one dose in order to reach the maximum efficiency. Okay, now the main message is when something strange is getting into our body, we have first the innate immunity, inflammation, activation of adaptive immunity, clonal expansion of B and T cells, antibody production, cytotoxic T cell proliferation, and memory B and T cells. Now we can address the first question: how does a vaccine work? Well, a vaccine is doing just one thing, is introducing an antigen into our body. All the dirty job is made by the immune system, exactly through the same signaling pathways that are activated during an infection. So by introducing an antigen, which again doesn't mean maybe the whole virus or the whole bacterial cell, it can just be one protein or a portion of a protein. By introducing an antigen in the right way, then innate immunity is triggered, adaptive immunity is triggered. We have a very fast, let's say, a very, how to say, weak um, adaptive immune response, meaning weak because there is no pathogen to fight. So we have activation of all this machinery, but then they die out very quickly because there is no infection, but we are producing the memory cells, which are giving us the long-term immunity. So a vaccine has to meet two basic requirements: to identify the right antigen and to, let's say, develop a way to present this antigen to the immune system. Anything else is done by our body. So you see that it's quite difficult to consider a vaccine something artificial, because the, let's say, the active principle, the core business of a vaccine is a natural molecule, something that is present in a pathogen, which is present in nature. Okay, so what about the first question? How can I select the right antigen? Well, of course, I need to know a few things. I need to know how the pathogen is invading our body and how the body is responding, so I can identify the antigen by studying the primary immune response. But as viruses go, there is actually a quite useful simplification that we can make, because basically in 99% of cases, the major antigens, meaning the portion of the virus that is triggering the most potent neutralizing immune response, are the surface proteins. And to understand this, we have to recall what a virus is, or let's say better, how a virus is composed. So viruses are not based on a cellular structure. They are intracellular parasites. We can think of viruses as sort of nano machines, very small machines that have just one function: multiply. They have just to copy their genes and diffuse them in the environment. So they are composed of a protein shell enclosing the genes, and the genome of a virus can be either RNA or DNA. Some viruses, they have also an outer membrane, which is a portion of the cellular membrane from which the virus is, escaped during, the replication process in the infected cell. And within this, let's say, stolen cellular membrane, the virus has embedded its surface protein. So either the protein of the protein shell, the capsid for naked viruses, or the surface glycoproteins are the major antigens recognized by the immune system. And what happens in the infected cells is when the virus enters, and many viruses, this is the SARS-CoV-2, are introduced in the cell through an endosomal pathway. So they are introduced enclosed in this small vesicle endosome. That's why the toll-like receptors are very often present on the endosomal membrane, because it's one of the main entry points for many viruses. Then they release their genome, and viral proteins are produced within the cell. And of course, these proteins are used to build up new viruses, but part of these are also destroyed, degraded, and the small pieces of these proteins are exposed on the surface of the infected cells, and they become antigens, which are then recognized by the immune system. So, as I said, in the case of viruses, the surface proteins are very often the most immunogenic. So it's quite easy to start to think about a vaccine for many viruses, because you always start from their surface proteins. Well, of course, you are not always lucky, but most of the time you are. And when you have a vaccine that is capable of inducing an immune response against the surface protein, what happens is that, for example, your antibody binds to the protein. And since these surface proteins are always those proteins that can engage the cellular receptor and allow the virus to infect the cell, by binding to the surface protein, the antibody prevents interaction with the receptor, so it prevents infection. While the T cell, cytotoxic T cells, they will destroy the cells that are already infected. Okay, so let's say we have identified our antigen, and in the last lecture, you will probably learn how we can, in the lab, really select the antigens. But we know the antigen, we now have to find a way to deliver it to the body. And there are many different routes that can be used to deliver a vaccine. Some, for example, can be introduced intranasally. You just breathe and you get, your antigen through the mucosa of your upper respiratory tract. Other can be ingested. For example, some, one of the polio vaccines that are used, it is taken orally. Most of our vaccines are intramuscular. So you have to inject them under your skin so that they can be taken up by the resident cells that then activate the immune response. And there are, of course, many different also systems that are, let's say, experimented. But the point is, the simplest, the route of administration, the most efficient, or let's say the most practical, is the vaccine for mass usage. So every time vaccination development tend to find the easiest way to administer the vaccine, because the concept of vaccination is to give it to a lot of people. So you need to find a way where you can administer it easily and hopefully without needing trained personnel, because one thing is to vaccinate people in the Western countries, one thing is to vaccinate people in the middle of the, let's say, jungle in some godforsaken countries in the third world, where, you know, the infrastructures are very weak. Well, how can I deliver now the antigen into the body through these many different routes? So there are very different techniques that are being used in today's vaccines. Some are very classic, I would say. You take the virus, the live virus, meaning that it can still replicate, but in the lab you make some, you know, trick, many passages in cultures, for example, so that you select an attenuated virus strain, meaning this virus can replicate, but it's weak, you know, so it cannot give you an acute infection. It cannot give you symptoms like the, let's say, wild type strain, but it can trigger immunity. You know, the live attenuated vaccines are to be used with great care because, especially for RNA viruses, it can be that when you start to vaccinate billions of people, they can retromutate, so they can become again pathogenic. This is what has happened in the last, you know, decades with the oral polio vaccine, which was based on a live attenuated virus. A particular strain that was used was able to retromutate, and in, I don't know, one case every 100 millions was able to give actually poliomyelitis. So now we have almost completely eradicated the wild type poliomyelitis, but we still have a few hundred cases in the world of vaccine-derived poliomyelitis, which is not a problem anymore now because the oral polio vaccine is not being used so often, because it was very important to, let's say, reduce, to curb the epidemics in large population. But now that we have very few cases, we are using the inactivated vaccine. And also from the oral polio vaccine used nowadays, those strains that have now been completely eradicated from the world are not used anymore. But we still have, you know, this kind of problem. And this is actually a demonstration that the live attenuated vaccine can work beautifully, but it can also have some drawback. So it's much safer to kill the virus. So you take the whole virus, you inactivate it chemically, so that basically you destroy it, and then you inject this mixture of all the viral components that can trigger, that can trigger the immune response. One drawback of this approach is that you are making antibodies against all the components, all the antigens of the virus, but only a fraction of those antibodies will be neutralizing, because antibodies made against some internal protein or proteins that are expressed only in infected cells might not be very effective in blocking the virus. So modern vaccines are preferring the use of purified antigens, which are much safer. They are much more, tolerable, and they can give you a very focused, a very specific immune response against the major antigen. So you clone the gene for that particular protein, then you express, for example, the protein, purify, inject it as a vaccine, and you will mount a specific immune response, very robust, against that particular set of antigens that you know are neutralizing. And that's precisely, for example, what is being done now for the SARS-CoV-2 vaccines. And we are actually using very sophisticated technological platforms, for example, using viral vectors. It's not nonsense using a viral vector in order to make a vaccine against a virus. Because what you do, you take a virus which is not generally pathogen to humans, for example, a simian adenovirus. Adenoviruses are causing sort of a cold, common cold, and you take some animal adenovirus, you delete from the genome of the virus those genes that are required for the viral replication, and you replace these genes with your exogenous gene, so the gene encoding for the antigen. Then you can assemble these defective viral particles in cell cultures, providing in trans the missing proteins that allow these viruses to be produced, but they incorporate a genome which is defective. So those viruses will not be able to proliferate, but they will contain in their DNA the gene for your antigen. So this replication defective virus is still able to penetrate into the cell, to open up its protein shell, the capsid, which is destroyed, but then it cannot produce new viruses. It can only release your foreign gene that will enable the cell to produce that particular protein, which will be then degraded, exposed at the surface, and then becoming an antigen for the stimulation of the immune system. So this is the concept behind the adenoviral vectors like AstraZeneca, Sputnik, Johnson & Johnson. The same idea, but with a different, let's say, technological platform, is behind the mRNA vaccines, Pfizer, Moderna's. So mRNA, I don't think I need to explain to you what it is the form, the chemical form of the genetic information which is produced 1,000 times every second in our cells in order to synthesize proteins. So the idea is to give directly to the cells the ready-to-use mRNA, which is required to synthesize the major SARS-CoV-2 antigen, which is the surface protein, the famous spike glycoprotein. So these mRNAs are, enclosed within a lipid nanoparticle in order to protect them. This lipid nanoparticle can fuse with the cell membrane. So when it is injected, it will be taken up by muscle cells, but also some of these nanoparticles will diffuse to the lymph nodes, and then they will be taken up by dendritic cells or specialized cells. Both the muscle cells or the specialized immune cells, they will then produce the spike protein, which is then degraded and exposed to the surface of the cell, where they can be recognized by the adaptive immune system cell. So as soon as this mRNA is getting into the cell and the foreign protein is produced, you have also innate immune response. So you have some local inflammation, which is lower in the case of the mRNA, because this foreign RNA, which is in principle recognized by the toll-like receptor, has been modified, optimized in order to be weakly recognized. That's why usually inflammation is lower in the mRNA vaccine, while in the case of the adenoviral vectors, the capsid protein acts as a very strong immunogen. So you might have a stronger inflammatory response, which is in a way a good thing, because it will boost the innate immunity, which in turn will be more active in triggering the adaptive immune response. So let's say that in this case, the capsid of the virus is acting as a sort of adjuvant. Okay, well, we can also create very sophisticated vaccines against other kind of diseases, not only infectious diseases. For example, we can make vaccines against cancer. So cancer cells are foreign cells. They are aliens. They have a, typical and unique karyotype. Every cancer cell have a different set of genes which are altered and has a different arrangement of chromosomes, which is completely different from normal cells. So cancer cells are recognized by the immune system as foreign entities because they express on their surface antigens, proteins that are different from those that are normally found in the body. So we can program in the lab T lymphocytes to recognize specifically those antigens that are expressed on cancer cells. Because, as I said, the T cell receptor is a protein. It is encoded by a gene. So once we know the antigen, we can select in vitro, in the lab, with the different techniques, population of specific T cells. We can clone the gene corresponding to the T cell receptor, and then we can take the T cell of the patient. We can engineer in them in order to make them expressing the receptor for the particular antigen of the particular tumor of that particular patient. And then we can reinfuse these cells that will proliferate and attack the tumor. So that's the so-called CAR-T, recombinant T cell receptor gene, or say anti-cancer therapy. Just an example of how we can play with the immune system in order to generate next generation vaccines. Now we have the vaccine, we start to vaccinate people, but what's the purpose of vaccination? Well, the purpose is to block the diffusion of an infectious agent. Infectious agents can be, classified in terms of their, let's say, speed of diffusion, which is normally expressed by this number, R naught, R null, which is a probability measure. It gives you the probability of having a certain number of infections coming from a single case. So for the SARS-CoV-2 virus, every infected person will, by mean, infect 2 or 3 additional people. And you can immediately understand that each of these people will infect 2 or 3 others, and so on and so on. And you have an exponential diffusion of the epidemics. Now, what the vaccination is doing is to change this R naught value into an RT, meaning changing the value with time. Why? Because as soon as you start to have an infection, you will start, for example, to have some people who, have passed the infection and now they are immune. And more immune people you have in a population, lower is the probability that one infected people will meet susceptible people to be infected. Now, if we can increase the number of immunized people without waiting for all the people to get ill and then, to recover, then we can reduce the probability of infection to less than 1, meaning for each case, we will have less than 1 additional case, or the epidemic will die out. So the concept of herd immunity is precisely this one. We need to create or to have a large number of immunized people in order to prevent, diffusion of an infectious agent starting from an infected person. And the percentage of people that need to be vaccinated depends on the R naught of that particular virus. So, for example, if you have an R naught equal 2, then it's enough basically to vaccinate about 70–75% of the people in order to be able to control, to let's say, reduce the probability of infection so that the epidemic will die out. However, if the R value is higher, then you will need to vaccinate an higher number of people. For example, with R equal 5, you need to vaccinate about 90% of your population. So that's why we say, in order to protect people from SARS-CoV-2, we need to vaccinate 70-75% of the people, because R naught is from 2 to 3. And this also tells you why vaccination is useless if people is not getting vaccinated. And herd immunity works. This is just to show you, the percentage of reduction of all these different kinds of diseases for which, is available a vaccine. This is for the United States, but it's the same, all over the Western world. You see, we have reduction from 100 to 85%, meaning that if you get enough people vaccinated, you stop the epidemics. And about the efficacy of the vaccine, this is just, this is just to show you the efficacy of the currently available vaccines against the SARS-CoV-2. You can immediately see that some of them are quite effective even already after the first dose. Efficacy here means protection from the symptomatic disease. Protection from death, or let's say a grave form of the disease, is about 100%. However, you see, some of them are very effective already after the first dose. Others reach the maximum efficacy after the second dose. The Johnson & Johnson vaccine from the clinical trials is not particularly effective. It's good, it's very good, but it's not as effective as the other ones. It requires only one dose, but then we will see in real life, maybe numbers will improve. So just to give you an idea that all three vaccines are very potent in preventing symptomatic diseases. They can also prevent infection overall at about 75-80% of cases, okay? And vaccines are safe, but in order to, convince people the vaccination is, safe, or at least risks are much higher when you get the disease than when you get the vaccination, you have to show numbers. I'm sorry, these slides are in Italian, but I just provided the essential translation in English. For example, mumps vaccination. So if you get mumps, in 1 to 10, in 1/10 over 100 cases, you can get meningitis, 1 to 4 orchitis, 1 to 1,000 encephalitis. You very often get reduced fertility if you get the illness when you're very young. If you get the vaccine, you might have some problem with febrile seizure in about 1 to 3 cases over 4,000. And you can have a transient thrombocytopenia in 1 case over 40,000. So you can see already, comparing these numbers, that any kind of risk you can get from vaccination is much lower of the cumulative risk that you can get if you get the illness. And the same is true for measles, even worse, because measles can have a 1 over 1,000 death rate. 1 over 20 can develop pneumonia, 1 over 1,000 encephalitis, while the, let's say, side effects are much rarer and also are much less dangerous. And also the meningococcus vaccination. Well, you will know meningitis very often is fatal, 1 over 10 death rate. But it can give you also permanent damage of very different kinds very often, while the severe allergic reaction from vaccination against the meningococcus is about 1 over 1 million. So now, if you can communicate this kind of message to people, then you let them decide. But I would say only a fool will take a 1 to 10 risk of dying instead of a 1 to over 1 million to have an allergic reaction. This is an old story. I don't want to get into details, just to remind you, vaccines do not cause autism. That was, a real fake news, a real, fabricated data set that has been demonstrated absolutely false many different times. So still people believe that vaccine, particular measles vaccines, can cause autism. That's absolutely untrue. And there is, an extensive scientific literature that can demonstrate this. Well, there is one small problem, that you make a vaccine against an antigen, which is a piece of a protein of a virus. And the efficacy of your immune response depends on the particular amino acidic sequence of that particular piece of protein, because the antigen is just a stretch of amino acid. If the amino acid change, then probably your vaccination is not going to work, or it's working less. The problem is viruses, particularly RNA viruses, have the bad habit of mutating very fast. This is just an example of the genetic diversity all over the world of the seasonal flu in 5 years. You can immediately appreciate that you start with this kind of virus and then you end up with this one, whose genetic diversity is more than enough to make the vaccine used here completely ineffective against this particular virus. That's why almost every year or every 2 years, we have to change the antigens in our flu vaccination because the virus is mutating. But we can do it. For example, thanks to the magic of biotechnology, well, the point is our vaccines are based on the two major antigens, which are again the surface proteins of the virus, hemagglutinin and neuraminidase. So the antibodies block infection because they block, the surface glycoproteins. You have a mutation, you have a different glycoprotein, your antibody is not working anymore. But flu viruses are made up by 8 RNA segments. Let's call them 8 chromosomes. It's not true, but just to give you an idea. So 8 pieces of RNA, each of one encoding for a protein or 2. And so, for example, there is 1 fragment encoding for the antigen. We know that. We can sequence that. We can understand where the mutation is. More difficult is when you have an exchange of more than 1 fragment. This is something that happens rarely, but it happens. And this is the reason why we can have pandemic influenza viruses. So it happens when 2 different viruses, for example, avian and human, avian and swine, they meet in the same host, typically swine, and then they exchange different segments. So they create a completely new, let's say, combination of antigens that human beings never have met. So if those viruses are able to infect humans, you have a pandemics. And we had 5 influenza pandemics in the last 100 years, thanks to these, big events of reassortment. However, again, we can isolate the virus, we can sequence the gene for the major antigens, we can understand where they come from, we can get those segments, and we can build a new vaccine because we can put each segment in a plasmid. We can put, for example, the new neuraminidase of hemagglutinin of the mutant virus together with the other plasmid encoding the standard genes. And then we can make a cell transfected with these 8 plasmids to build a new virus that then we can use for vaccine. We can destroy it, we can purify the new antigen, whatever. So it's quite easy now to make version of a vaccine that can deal with mutants. And SARS-CoV-2 is an RNA virus, and it isn't an exception. It mutates. So these colors represent the 8 major genetic families of SARS-CoV-2 currently circulating all over the world with different, different frequencies. And within each clade, you have the variants. Again, viruses with small genetic differences. Now it's clear sometimes these differences can happen at the level of the major antigen, that is the spike protein. This is the case of the 3 major variants we are all, let's say, hearing about in the press. The variant isolated in the United Kingdom, the variant isolated in South Africa, the variant isolated in Brazil. Now, these viruses have accumulated amino acidic substitution in these 2 domains of the spike protein. This is just a representation of the 3-dimensional structure of the spike protein in 2 different, flavors, but it's the same. So this N-terminal domain and this receptor binding domain are those parts that are more, let's say, mutated in this variant. And particularly these substitution, position 501 and position 484, are responsible for a reduced ability of some antibodies to bind. However, if you look here, you have many different color patches on this protein. What are they? Those are the portion of the spike which are able to trigger an immune response. These peptides are the antigens that have been recognized by the immune system, which produce antibodies able to recognize them when they are, of course, part of the entire protein. Just to tell you, when an antigen, a stretch of amino acid that has been an antigen, is part of the native protein, it's called epitope, but it's the same. Is the place where the antibody will bind. Now, you can immediately see that while some mutations probably will reduce binding of an antibody here and here, all the other parts are still intact. So, probably, vaccine might be still able to protect against these variants because they trigger antibodies against all these portions of the protein. And actually, this is the case. So this is the efficacy of the Pfizer vaccine against, let's say, the wild-type virus and the different variants. Simply, the height of this bar indicates the amount of serum of immunized people that you require to reduce by 50% viral proliferation. And the point is, you see that against variants, the height is almost the same. There is just some reduction against the South African variant, but this is the level, below which you have no protection. So still, you have a significant neutralization activity against all the variants, all the major variants that are circulating. So if you then do the trick, if you look at each single epitope, so each portion of the protein that can work as an antigen, and in this case, those that are recognized by the TCD8 lymphocyte, those lymphocytes that kill infected cells, and you look at what the effect of the mutation is at each of these epitopes, well, you can see that in most cases, you have no effect for all 3 variants. In some cases, you even increase the ability of the T cell to recognize the infected cell, and in another number of cases, you reduce. So overall, these mutations do not impact significantly also on the ability of CD8 T lymphocytes to kill the infected cell. That's good news. Now, for AstraZeneca, we have right now only data about the UK variant. But these are good data because looking at vaccinated people, then, got infected, and sequencing, let's say, looking at people vaccinated and not vaccinated and making, the proportion of those that were infected in vaccinated versus unvaccinated, sequencing the virus in order to understand how many they were infected by the variant or by, other circulating strains, you can see that the efficacy, so prevention of symptomatic disease, was almost identical between the variant and the other circulating strains. And also, what you see here is a measure of the amount of virus in the respiratory tract of vaccinated or unvaccinated people infected with the variant or with the other strains. This is actually the number of PCR cycles required to detect the RNA of the virus. So the higher the number, the lower is the amount of the virus. As you can see that consistently vaccinated people have higher CT values, meaning lower viral loads than unvaccinated people, both when infected with the variant or with other circulating strains. So AstraZeneca can protect against major circulating SARS-CoV-2 variant in Europe. Okay, I'm done, and that's the last slide. I'm sorry, maybe I was too long, but hope you didn't get bored. This is the final message. So in your medical profession, you will have to make counseling to people about vaccination. And you will meet two kinds of people. You will meet those who hesitate to be vaccinated, and you will meet those who don't want to be vaccinated. Now, those who are, let's say, ideologically against vaccination, the so-called no-vax, you cannot, convince them. Believe me, I tried for many years. You can give them, the best science, but they will just not listen to you. What you have to do, because that's the largest amount of population, is to confront with the hesitancy those people who still don't understand why they should inject themselves with something they don't know nothing about in order to prevent a risk they are not able to quantify, a risk of getting an illness that maybe will not even cause any damage. So you will have to be prepared to explain in a respectful, clear, and very, let's say, data, solid data way, how a vaccine works, what are the risks, what are the benefits, and then let people decide. Because it's not because you will have, wearing a white coat that people will believe you, not anymore. So one big part of your profession, particularly regarding vaccination, will be communication. So let's say train also in communicating with the many different kind of people you will encounter in your medical profession, because building trust between the doctor and the patient is the first step to get an effective therapy. Okay, so thank you very much. And now I'm just quitting my presentation, and if you are not sleeping, I can answer to all of your questions. Thank you.
Thank you very much, Professor, for the very comprehensive explanation. And there is a number of questions in the chat. I will be reading them to you. I don't know if we'll have time to go through them all. So maybe the questions that are more specifically pertaining to vaccines, you can save them for the last conference of the cycle that, as we said before, will be specifically on that topic. So the first question is from Silvia Costa, and this question arrived when you were explaining the different ways of delivering the antigen would like formulating the vaccine, so how to deliver the antigen. So she asks, how is the mRNA modified to lower the innate immune response?
Yeah, so basically in two ways. First of all, you have to consider that sometimes the codon usage of meaning of the kind of codons that are within a viral genome might not be the best for expressing a protein in a human cell. That seems to be counterintuitive because human viruses, they infect human cells. But, well, first of all, this is a new virus, so probably it's not, let's say, so well adapted. But also sometimes even flu viruses, they use rare codon usage as a mechanism of regulating protein expression. I can't go into details, but the point is, sometimes you have to change the codons in order to maintain the same meaning, so the same amino acid, but in order to have a more, a frequent expression because you have the corresponding tRNA, which is more abundant in the cell. Then you can chemically modify the basis of the RNA, because it's known that some chemical modification, they lower the ability of the toll-like receptor to bind this RNA, but they do not impact on the ability of the ribosome to translate it. Then you can also add some stabilizing untranslated sequences in order to improve the half-life of the mRNA. So overall, what you have is not the endogenous mRNA of the virus, but a version which is optimized for being expressed for a few days in the cell without triggering a very strong innate immunity.
Thank you. The next question from Martina Consigli. She's asking, cannot the adenovirus be used to carry the that is used to carry the viral antigen be recognized by the immune system and destroyed?
Oh yes, very much. That's why actually a few vaccines failed, because they were using as a vector a human adenovirus of a very common serotype, for example, adenovirus 5. And one of the most heartbreaking failures has been a few years ago, a phase 3 clinical trial of an HIV vaccine based on adenovirus 5, where it was, everything was stopped because the researchers realized that vaccinated people had a higher risk of being infected by HIV. So quite the opposite. The reason was most of the people in that particular area of the world, it was the Southeast Asia, they had a strong immune response against this very common serotype. So the immune system was killing the vector, which was not delivering the antigen. At the same time, by stimulating the helper T cells, they were more easily infected by HIV. So that's an example, sometimes how careful you must be in designing this type of vaccine. That's why now either you use animal adenoviruses for against which you don't have immunological memory, or you use a very rare human serotypes. So you mount an immune response, but which is not let's say fast enough to destroy the virus, because it is a non-replicating virus. So the virus enters, if you don't already have antibodies, it will infect the cell, deliver the gene, and then everything stops. So then you can get a higher efficiency.
Thanks, Professor. Next question is from Deborah, and she's asking, what determines the fact that some people are non-responders to the vaccination if they still are immunocompetent?
Well, that's basically related to the differences that we have in our genetic constitution. So you can be immunocompetent, generally speaking, but for some reason, your immune system is not presenting in an efficient way that particular antigen. So you are not responding. And it really depends on, by chance, the fact that maybe you don't have the right combination of major histocompatibility complex receptors that can recognize that particular antigen. Sometimes because by chance that particular combination has been, let's say, deleted during the maturation of the B and T lymphocyte because in some way was, let's say, was recognized as a self-reacting combination. So it's rare because I think non-responders are within 1-2% of vaccinees, but it can happen. And it's just a matter of chance, you know. If there are no pathological conditions that can explain this, it's just a matter of being unlucky.
Thank you. The next question is from Sylvia. She's asking, how can the Johnson & Johnson vaccine provide protection with just one injection?
Because likely the formulation and the amount of antigen that is being injected are enough to provide a strong immune response, strong enough to protect, as I showed you, 66% of people vaccinated from symptomatic disease. It's not stellar, I would say, and maybe in real life, if we will see that the efficiency is maybe lower of that level, it might be that a second dose will be tried. But you have, of course, to have a clinical trial and also for a 2-dose regimen. If protection is of the range of 65-70%, even not spectacular, it will be very highly significant in terms of mass vaccination because it will anyhow reduce significantly the risk of symptomatic infections, and being a single dose will allow you to vaccinate a lot of people very quickly.
Understood. Then there is still on the topic of the vaccine doses, Delal asking, how is the time in between first and second dose of vaccination decided, and why does it differ in different types of vaccines?
So normally you select the dosage, let's say, during the phase 1 and phase 2 clinical trials based on the immune response. So what you do, you try different schedules of administration, and then you measure the antibody response in the people vaccinated, and you select, you know, the let's say the most effective dosage, and then you try it in the phase 3 clinical studies. Maybe you try already a couple of different combinations, and in the end you decide. So it's just a matter, of course, of trial and error, and it comes from the preclinical study when you challenge the animals and you know, start to, let's say, understand how many boosts you need to have a strongest response, and then in the first 2 phases of clinical trials you try it on humans and adjust, you know, the dosage in order to have the most potent immune response. And of course, different among different vaccines because you might have different formulations and different potencies also depending on the antigen.
Thank you. Then we have Lorenzo asking, how did the 1980-20s Spanish influenza pandemic come to an end without the use of a vaccine? As far as we know, did different variants rise also back then? If so, how did they impact the pandemic?
Okay, the Spanish pandemic, which was not Spanish, by the way, it came from the United States. Probably it came from Asia to the United States and then to Europe during at the end of the First World War. Came to an end after killing 100 million people. As simple as that. Every, you know, viral epidemic will die out sooner or later, either because it has killed all the people that can be killed and the other, you know, recovered and became immune, or because it mutated maybe and became less pathogenic. For sure, there were variants, but the point is we were not able to sequence RNA viruses, not even DNA viruses. We didn't even know, very well how DNA was, because in the 18th, 19, the structure of DNA was not known, as you well remember. So we know the genome of, let's say, a strain of this virus that has been derived from bodies interred in Alaska in the permafrost, so they have been conserved. And at the end of the 90s and the last century, some researchers, they were exhumating these people and isolating the genetic material, sequenced it, and now we have the sequence of one strain. But of course, as always, flu viruses mutated, so probably there were different strains. And it might also be one of the reasons why these pandemics had different waves. We are now talking about waves of SARS-CoV-2, but it's not correct, because we never, let's say, went out from the first wave. The virus was circulating all the time, and all these differences we see are just the result of the measures that we are, putting in place, lockdowns and blah blah blah. While the flu was seasonal, even in the pandemic, so there were different waves. The second was worse than the first, so maybe there were different strains acting at the time, but we don't know.
Thank you. I think we can take the last three questions, and then we can conclude the conference. So we have from Nadia: could these vaccines create issues if a person has some specific disease already?
Okay, so there are very, very few pathologies that prevent vaccination, mostly of allergic nature, but severe allergic nature. Some autoimmune disease, like sarcoidosis, must be evaluated by, by the clinicians. But most of the chronic pathologies, even quite serious one, cancer, cardiomyopathy, whatever you can think of, they are not preventing vaccination. On the opposite, those people who are immunodepressed or who have chronic diseases or oncological patients, they must be vaccinated, because they are at very high risk if they get infected.
Okay. Then we have Gloria asking, what would happen if I already have the antibodies and got the vaccine?
Probably nothing. I mean, I say probably because the point is vaccination in a recovered patient could be seen as a boost. That's why now the guidelines, they, let's say, prescribe a single shot for people who have a known history of the disease. A single shot between 3 and 6 months from the recovery. But even if you maybe were asymptomatic, so you don't know, and you get the vaccination and you still have the antibodies, basically it shouldn't happen anything. You might have some more intense, secondary reaction, but there are no, let's say, known cases of serious adverse events in recovered people who got vaccinated.
Thank you. And I think we can take now the last question from Aaron, which says, do you think that being vaccinated, for example, with a first shot of AstraZeneca and then with a second shot of Pfizer is possible? And do you think that doing so can theoretically affect the final efficacy?
So I think in the UK, there is a clinical trial ongoing for this mix and match approach. So the honest answer is we don't know. In principle, shouldn't make a big difference, because the concept of the vaccine is the same. You deliver a gene in order to make the antigen. Of course, the delivery system is different, so we don't know whether an immune system which has been stimulated, for example, by a viral vector, will react in a different way if it is boosted by an mRNA. So it might also be not as efficient as, a boost with the same vaccine. So I would say maybe it's safer to mix AstraZeneca and Sputnik, so to speak, because they are both based on the same platform, adenovirus. But you know, we have no data, so it's very difficult to answer.
Okay, I think we can conclude now the conference. I would like to thank you, Professor, for accepting to participate in this first conference. And I think I speak for everyone when I say you were very clear in your explanation and you replied very clearly to the questions. So thank you for contributing to our cycle of conferences. And I remind everyone that this is not an isolated event. We have a complete cycle of conferences to approach the topic of vaccines. So please check out the remaining conferences of the cycle and try to attend if possible. And yeah, have a good evening. And thank you again, Professor, for helping into making this happen.
So if I can have the last words, it has been a pleasure. It's always a pleasure to see, you know, young students willing to learn one of the most fascinating profession. I'm not an MD, I'm a biologist. My daughter is studying medicine now. So let's say my very best wishes. And just remember, your one is not a job, your one is a vocation. So just, you know, do it with passion, because it's, you know, one of the pillars of our well-being to have educated medical doctors. So thank you very much.
Thank you, Professor. Good evening,
Bye-bye.
everyone.
Good evening.
Bye-bye.
Good night.